Hi folks, this is Shefik. We have recently mentioned Elliptic Curve ElGamal encryption algorithm. I would like to mention this algorithm comes with partially homomorphic features, but the length of that video reached 20 minutes. That's why I want to split the content and mention its partially homomorphic features in a separate video. But before we begin, please like the video and do not forget to subscribe to the channel to stay up to date with the latest videos. Also, your comments are more than welcome. Thank you for your all support in advance. Regular ElGamal algorithm was multiplicatively homomorphic, but we can modify the algorithm and we can make it additively homomorphic. On the other hand, elliptic curve ElGamal algorithm is additively homomorphic. Let's explain why the crypto system is homomorphic with respect to the addition. First, if we encrypt the message 1 and 1 with the random key R1, we are going to have 2 points and our ciphertext is going to be random k1 times base point g. This is going to be our first point and it comes with x and y coordinates, and the second point is going to be random k1 times q. Here q is the public key plus message 1 times base point g. Secondly, if we encrypt the second message M2 with random key R2, we are going to have this point pairs. The first point is going to be R2 times base point G, and second point is going to be random key 2 times Q, which is the public key, plus message 2 times base point G. Now let's find the sum of these two ciphertexts. To perform this action, we are going to add the first point in our first ciphertext to the first point in our second ciphertext. Similarly, we are going to add the second point in our first ciphertext to the second point in our second ciphertext. And addition becomes random k1 times base point g plus random k2 times base point g. This is going to be the first point, and the second point is going to be random k1 times public kq plus message 1 times base point g plus random k2 times public kq plus message 2 times base point g. In our first point, the both elements have base point g multiplier. That's why we are able to represent this as random k1 plus random k2 times base point g. Similarly, in the second point, two elements have public kq multiplier and two elements have base point g multiplier. That's why we are able to represent this as random k1 plus random k2 times public kq plus message 1 plus message 2 times base point g. This is the addition of two ciphertext values. On the other hand, if we find the addition of two plain messages and we encrypt this addition with the random k1 plus random k2, we are going to have the same value. This shows why elliptic curve ElGamal algorithm is partially homomorphic with respect to the addition. Let's implement the partially homomorphic features of elliptic curve ElGamal algorithm in this notebook. You might remember that I written that notebook in the recent video. Here I'm going to create a common encrypt function because I'm going to use it in many places. This function is going to get input message and also random key R. In this encrypt function, we are going to find the point as first. Thereafter, we are going to calculate the points C1 and C2. And finally, this function is going to return C1 and C2 pair. Thereafter, we are going to call this anchor function and pass message and random key as input, and this is going to return C1 and C2. Let's see everything is okay. I'm going to run them all. This cannot print the variable s because s was calculated in this anchor function. Let's recalculate it and set it to s real. Print s real. Here s prime and s real are equal to each other, so we can check this. Now I'm going to focus on the homomorphic features, actually partially homomorphic features. Here I'm going to encrypt two messages. First message is going to be 333 and second message is going to be 777, and I'm going to need two different random keys R1 and R2. And here I'm going to call random dot generate random bits, and I'm going to generate 256-bit random key for random 1, random 2 case. Then I'm going to encrypt message 1 and random key 1 pair and pass message 1 and random 1, and this is going to return C1 and C2. Let's set this to X. Similarly, I'm going to encrypt message 2 and random K2, and this is going to C1 and C2 for Y values. Here C1x, C1y, C2x and C2y, they are all points on our elliptic curve, and I'm going to find the addition of C1x and C1y. This is going to be the first point. Thereafter I'm going to find the addition of C2x and C2y. This is going to be the second point. To find the addition of two different points, I'm going to use this at points function, and here first point is going to be C1, second point is going to be C1 again, but first one was C1x and second one was C1y. Finally, modulo is going to be P, and I'm going to find the addition of C2 values at C2x to C2y. This is going to be my point pair. Finally, I'm going to set this calculation to message 1 encrypted plus message 2 encrypted. Let's see the content of message 1 encrypted plus message 2 encrypted. It consists of 2 points. On the other hand, if I encrypt message 1 plus message 2, those messages are plain messages, and this addition is going to be a plain message. I'm going to encrypt the addition of those two plain messages with random k1 plus random k2. As you can see, they are both equal to each other. I can check this like that. This shows the partial homomorphic features of elliptic curve ElGamal algorithm. It doesn't matter, you can either find the encrypted values of two plain texts and add them to each other, or you can find the addition of two plain texts then encrypt it. They both give you same message, because this crypto system is homomorphic with respect to the addition. Thank you all for watching, and see you next time.